Hello, I'm Heewon Park in Seongshin Women's University, Korea, and Tokyo Medical and Dental University, Japan. I will talk about the statistical methodology for uncovering COVID-19 severity marker. My talk will be given in the following 5 parts. At first, I will introduce the motivation of our study. So as we all know, the COVID-19 virus has been spreading and caused millions of deaths in the world. Especially COVID-19 severity is deadly disease. So to uncover COVID-19 severity mechanism, many studies have been conducted. I think, however, there are critical limitations in the existing study. That is, the most previous study focused only on the perturbation of single genes. However, the complex mechanism of COVID-19 involves several genes that interplay in the molecular networks. So molecular interplay rather than the abnormality of a single gene should be considered to identify COVID-19 severity mechanism. So in our study, to identify the COVID-19 severity mechanism, we analyzed whole blood RNA sequence data from Japan COVID-19 task force. And then we construct COVID-19 severity specific gene networks. Let's move on the methodology part for the networks analysis. The gene networks is similar to the human community and human networks in the company and community. I mean, gene networks is to describe the causal relationship between genes and usually estimated by expression level of genes. And from these estimated gene networks, we can identify the phenotype-specific molecular interplay. For instance, COVID-19 severity-specific molecular interplay. And this phenotype-specific molecular interplay provide a crucial insight to understand complex mechanism of disease. So to estimate gene networks, many statistical and computational methodology were developed and have been used to gene networks analysis. However, after gene network estimation, we hit the wall in interpretation of these huge gene networks. Actually, the estimated gene networks are given as matrix form, consisting of more than 10,000 genes and more than 10,000 row and more than 10,000 column. So interpretation of this huge network by human eye was impossible. I mean, gene network interpretation was very hard task for me. So to settle on this issue, we propose one idea to interpret these huge gene networks. Let's consider there are two phenotypes, for instance, COVID-19 severe and non-severe sample. In this case, the subnetwork 1 and 2 can be considered as a common network for two phenotypes, and subnetwork 3 and 4 can be considered as a COVID-19 severity specific molecular interplay. So in our study, we aim to identify these COVID-19 specific gene networks. To do this, we propose a statistical methodology that measure the similarity between gene networks. So at first, I will introduce some notation used in our study. Here, X and Y are M/P metrics to describe the expression level of gene in phenotype A, phenotype B, respectively. And we assume that this expression level of genes are generated from multiplied normal distribution. Usually, the precision metrics are used to describe the gene networks and given as inverse of variance covariance matrix. So in this case, the weighted graph for phenotype A, phenotype B can be given by GA and GP, so where V and E are set of node and set of edge respectively, and W is to describe the edge weights. So for the differential regulated gene network analysis, some computational methodology were developed. The first methodology is SAMGS, that measures the similarity of networks based on difference of mean of expression level of gene included in the networks. And second methodology is gene set co-expression analysis. This methodology measures dissimilarity of networks based on difference of correlation coefficient between genes, where CKJA and CKJB indicate the correlation coefficient between gene K and gene J in phenotype A and phenotype B respectively. Although this methodology have been widely used for differentially regulated gene networks analysis, the existing methodology based only on the information of expression level of genes. However, not only expression level of genes, but also network structure is a crucial information to describe gene networks. So in our study, we proposed a statistical methodology called the differentially regulated gene network detector that measures dissimilarity of network based on not only expression level of gene, but also network structure. So to measure dissimilarity of gene networks, we consider this Kullback-Leibler divergence that measures closeness between the probability distribution with density function fx and gx. And it has this property. It means Kullback-Leibler divergence is always positive and is equal to 0 if two density functions are identical. So in our study, for two gene network for phenotype A, phenotype B, we first define the probability density function fx and gx, where the variance covariance matrices are estimated by gene networks. Then we then measure dissimilarity between the networks based on closeness between these two probability density functions, like that. It means in our study, the dissimilarity of gene networks were measured by not only expression level of genes, but also network structure. And large value of Kullback-Leibler divergence indicate two gene networks show the different molecular interplay. And to assess the significance of this similarity of network, we consider the permutation framework. I mean, from the permutated expression level of genes, we estimated two gene networks. Then we then compute permuted Kullback-Leibler divergence for instance, 500 times. And then we compute permutated p-value. That is overall process of our strategy. Okay, let's move on the Monte Carlo simulation. For the two phenotype, for instance, phenotype A, phenotype B, we consider 5 common subnetworks, and each 5 phenotype A, phenotype B specific network were also considered. And each subnetwork consists of 10 genes, and their regulatory network structure are randomly generated by human-generated function in R package. So for scenario 1, 2, 3, and 4, we generate precision matrix with random, scale-free, hop, and cluster graph structure. So in our study, we aim to identify the phenotype A specific gene networks that we then generate expression level of genes based on generated precision matrix. And we also consider the various situation of mean and variance of expression level of genes. I mean, in situation 1, we consider not a deal of difference between mean vector in phenotype A, phenotype B. In situation 2, we consider large difference of mean. In situation 3, consider large difference of mean and large variance of expression level of genes. This table shows the result of phenotype-specific gene network identification. So as you see, the 3 methodologies show the similar result in the situation for the large difference of mean vector. However, the GSCA showed the poor result in the situation for the large variance. And in the situation for not a deal of difference of mean vector, same GS show the poor result. On the other hand, our methodology showed a stably effective result in all situations. Okay, let's move on the COVID-19 severity specific molecular interplay identification. As I told you, to identify COVID-19 severity specific gene network, especially in the Japanese population, we perform differentially regulated gene network analysis based on data from Japan COVID-19 task force. For the severe and non-severe sample, we first estimated 2 gene networks. We then applied our methodology and then identified 46 differentially regulated gene networks. Then we focus on the COVID-19 marker that were identified in the previous study of Japan COVID-19 task force. We call this marker as a J-COVID marker. And from the identified 46 differential regulated gene networks, we extract 15 networks that consist of at least 1 J-COVID marker. These figures show the identified differential regulated gene networks between J-COVID marker in severe and non-severe sample. Now we focus on these 3 large-scale gene networks. The first subnetwork consists of 25 genes, where only CETA was J-COVID marker. And HLA class 2 dominate the subnetwork 1, and their interplay become weaker and disappear in non-severe sample. Especially interplay between CETA and HLA class 2 was observed in only severe sample. It means this identified subnetwork 1 can be considered as a COVID-19 severity specific molecular interplay. And subnetwork 3 comprised of 26 genes, of which 21 genes were J-COVID marker. And only 5 genes were newly suggested as a regulator and target of J-COVID marker. This finding implies that the subnetwork 3 can be considered molecular interplay between the J-COVID markers. And to identify COVID-19 severity specific molecular interplay, I mean to identify biological function of COVID-19 specific molecular interplay, we perform KEGG pathway analysis for the subnetwork 1. These 3 pathway, I means antigen processing and presentation, and allograft rejection, and type 1 diabetes mellitus were the most enriched pathway for the identified COVID-19 severity specific molecular interplay. So our results can be summarized there. First, the HL class 2 and CETA are crucial marker for understanding COVID-19 severity mechanism. And second, the interplay between CETA and HL class 2 may play a key role in the mechanism of COVID-19 severity. So through this result and literature review, we can suggest the controlling the molecular interplay in the subnetwork 1, especially HL class 2 and CETA, may provide the crucial clinical insight to understand the COVID-19 severity mechanism. Okay, that's all.
You identify several networks.
Yes.
Subnetworks.
Yes.
Does your method automatically identify subnetworks? Well, did you examine the subnetworks from KHG database or some other database?
Yeah, no, our methodology automatically identified the subnetworks. Then we use the KEGG pathway for the interpretation of the result.
Okay, any other question or comment? Okay.
So, that 46 gene.
46 gene, yes.
So, have you checked like all those genes are upregulated or downregulated at this condition?
Downregulated, pardon?
Or upregulated at this condition? And COVID-19 time, so you are saying this 46 different regulated genes.
Networks. 46 networks.
Okay.
This is 46.
Okay.
Okay.
So how many genes are there?
No, I didn't check about the number of genes.
Okay. So have you any information that how many genes are actually upregulated and how many genes are downregulated?
No, I didn't check about that.